In flight, when a twin-engine aircraft has one engine inoperative and the other one at maximum thrust, it has a tendency to yaw towards the failed engine. In order to maintain the heading, the pilot deflects the rudder to create a yaw moment in the opposite direction. When the speed decreases, the operative engine delivers more or less the same thrust. To maintain the aerodynamic forces on the fin and the rudder, the deflection of the rudder must be progressively increased. At a given speed, it reaches its stop, and it is just able to counteract the effect of the engine. We're at the limit of control authority. On any twin-engine aircraft, below this speed, there is a risk of loss of control of the plane in case of failure of one engine with the other one at maximum thrust. The situation is similar for a quad with the outer engine failed. In flight, there are several minimum control speeds, or VMC. For takeoff configurations, it is called VMC-A, with A for airborne. For approach, we have VMC-L, with L for landing. On a quad, VMC-L-2 is associated with the failure of two engines on the same side in approach configuration. Everything is not black and white, and it is not because the aircraft is flying below a VMC that it will crash. But what is sure is that when reaching the VMC, the aircraft has very limited maneuvering possibilities. The pilot cannot do what he wants due to the fact that the rudder is on the stop and any roll maneuver creates side-slip. Some rules for the determination of the VMCs are rather odd, but they started to be used a long time ago, and safety is proven by the long experience on a huge number of flight hours on all aircraft types. By definition, the VMC is obtained when flying with a bank angle of 5 degrees towards the operative engine at maximum thrust, rudder on its stop, maintaining a constant heading. This bank angle is important as it allows a reduction of about 5 to 10 knots of the speed obtained compared to the same test performed wings level. For all VMCs, the test begins by the static measurement of the speed. It is then followed by dynamic tests to demonstrate that the maneuverability in roll remains sufficient at this speed, and that a sudden engine failure does not lead to a loss of control. The static test starts about 20 knots above the estimated value of the VMC. The aircraft is prepared with one engine shut down. The thrust of the other one is progressively put at its maximum while starting to decelerate slowly. During the deceleration towards VMC, the pilot keeps a constant heading. The rudder deflection increases as the speed decreases, eventually up to the stop. Further deceleration needs some bank towards the live engine to keep the heading constant. The VMC is obtained when the aircraft is stabilized with a constant heading, 5 degrees bank, and the rudder on the stop. The bank angle is difficult to stabilize because with the rudder on the stop, the yaw damper lacks authority on one side, and therefore there is a slight roll instability. To get a valid test point, the speed, the heading, and the bank angle must be very precisely maintained for about 10 seconds. As the 5 degrees value is never perfectly achieved, several measurements are performed with different bank angles above and below, and it then allows the precise value for 5 degrees to be computed. The VMC demonstrations have to be performed in the worst situation, and consequently, tests are carried out at very low altitude, in order to get the maximum thrust on the live engine. On some aircraft, it may be possible to perform the static measurement by setting the engine at a minimum idle thrust instead of shutdown, thanks to a specific procedure. Corrections are then applied by the design office. Various dynamic maneuvers must also be performed for the certification. Let's take the example of the roll maneuver for the VMCL. The rolling capacity is reduced on the side of the deflection of the rudder towards the operative engine at full thrust. But the regulations require that, stable at VMCL, it should be possible to roll through an angle of 20 degrees on the side of the operative engine in less than 5 seconds. Whatever the type of aircraft, there are risks in this test. Since the rudder is already fully deflected towards the operative engine, the additional side slip created by the roll maneuver cannot be counteracted, and it increases very quickly. Therefore, the roll command on the stick must be carefully adjusted. A rapid buildup of side slip could lead to a loss of control should it exceed a critical value around 17 degrees. Starting the test stable with 5 degrees bank, when passing 25 degrees, the recovery must be immediate and very smooth, with roll command neutral, the operative engine reduced to idle, some stick forward to increase the speed. The side slip must be carefully minimized, as it may become critical. The regulations require the demonstration that a sudden engine failure at VMC is controllable. As an example, a twin engine is stabilized in climb full thrust on all engines at VMC. One engine is quickly set to idle. The speed decrease is very fast. The pilot must react immediately with the pedals to deflect the rudder in order to control the yaw and to reduce the side slip. Simultaneously, he pushes the stick forward to minimize the speed decrease. The reaction must be fast, as otherwise the association of large side slip and very low speed could lead to a loss of control. The critical issue in VMC tests is the execution of the dynamic maneuvers, as it could very quickly lead to a loss of control because of the rapid buildup of side slip.